Welcome to the deep dive. We cut through the noise to get you the insights you need. Okay, picture this. You give your smartest AI assistant, a complex job at work, maybe processing leave requests, onboarding someone. It seems straightforward, multi-step, but then you watch it just stumble.
Yeah.
Or get lost. Sometimes it falls apart completely.
Yeah, that's a familiar story.
It's more than just frustrating, right? It really blocks businesses from getting the full power out of AI. So the big question we're tackling today is this. How do we get these super powerful AI tools to actually do these complex multi-step tasks consistently without getting lost or making silly mistakes or just, failing?
That's exactly the challenge. The core issue for these LLM agent systems, especially in real-world business settings, is they often just don't have the specific domain knowledge they need.
Okay.
And that leads to plans that are, frankly, disorganized. They might overlook really crucial tools.
Like tools needing special permissions.
Exactly. Permissions, or maybe tools that generate complex models or reports. And this leads to, well, unstable execution. The usual planning models, they just struggle to integrate reliably when you layer in all those business-specific details, those permissions.
Right. And that's precisely where today's focus comes in something called routine. We're diving into this novel framework. It's structured, designed specifically to bring stability, precision to these LLM agents in those messy real-world scenarios. So our mission here is to unpack how routine actually works, look at the performance impact, which is pretty surprising, actually,
Yes.
and figure out what makes it so effective. Why does it make these agents reliable for those multi-step business tasks you face? We're pulling out the key nuggets from the latest research for you. Okay, so let's lay the groundwork. LLM agents, we talk about them a lot.
Yeah.
What's the basic setup, the architecture?
Yeah, so typically you've got four main parts. There's the planning module, the execution module, the tools it can use, and its memory. And large language models, LLMs, are often the engine driving these, which makes them great for general stuff, summarizing text, answering broad questions, that kind of thing.
But the enterprise world, that's a whole different beast, isn't it? Where do these general-purpose LLMs start to fall short?
Oh, absolutely. They definitely do. In real business situations, these general LLMs often trip up because they're missing that specific process knowledge.
Can you give an example?
Sure. Think about an HR agent. It's trying to handle, say, a specific type of leave request, but it doesn't really understand the company's detailed step-by-step policy for that exact type of leave.
Right, nuances.
Exactly, the result. The plans it makes are disorganized, maybe even wrong. And like we said, they might just completely overlook vital tools. Maybe a tool that needs permission verification before it touches sensitive employee data, or a tool for generating a complex compliance report.
So it's not just about knowing that a tool exists, but it's the how and when, the specifics of using it in context.
Precisely. And another problem is inconsistent tool descriptions. In real companies, the way tools are described can vary. This makes it super hard for the models to reliably pick the right tool and the right settings, the parameters.
Which leads to
Unstable execution. Things just don't work reliably. Plus, current agent planning often doesn't have a unified, structured format.
What do you mean?
Well, the planning part might just pass some custom informal notes to the execution part, and then the execution module has to kind of guess what tool calling instructions it's supposed to follow.
So there's ambiguity, a mismatch between plan and action.
Huge mismatch potential. Yeah. And sure, there are low-code platforms trying to help with this, but even they often need a lot of manual setup and tweaking, so it limits the real efficiency gains.
Okay, problem crystal clear. General LLMs plus enterprise complexity equals instability.
Pretty much, yeah.
So let's bring in the solution. Routine, what is it, fundamentally?
So routine is essentially a multi-step planning framework for these agents. Its real strength is its clarity, clear structure, explicit instructions, and it handles passing information between steps, parameters really smoothly.
Okay.
Its main job, its core purpose, is to guide the agent's execution module to make sure it can perform those complex multi-step tool calling jobs with really high stability.
Okay, let's make it concrete. Walk us through an example. Say you, the user, ask something like, how many people are working on Project X? What happens then with routine?
Okay. So first, typically an expert provides an initial draft plan, like a high-level idea of the steps needed.
Like a basic recipe outline.
Kind of, yeah. Then a planning model takes that draft and refines it into a properly formatted routine. This routine is detailed, structured.
Got it.
Then this routine gets passed over to an execution model.
The doer.
Exactly. The execution model uses the routine like a step-by-step guide. So for your question, it might first call a tool like get projected to find the ID for project X. Then, using that ID, it calls another tool, maybe get participants, to get the actual list of people.
And
then finally, the agent puts it together and gives you the answer.
so it's like giving the AI this super detailed, almost foolproof checklist. What are the actual pieces, the building blocks of a routine?
Yeah. Think of it like this. Each step in a routine has key parts. There's a step number, obviously, for the sequence.
Makes sense.
A step name, just a short label for what the step does. Then, crucially, the step description. This is where the detailed instructions go. Conditions, objectives, what needs to happen.
Okay, details are key there.
Definitely. You can also have input and output descriptions for parameters. They're optional, but often really helpful. And maybe the most critical bit, the step tool. It explicitly names the single function tool to be used for that specific step.
That sounds really structured, almost rigid. Does that create issues? Like, can it adapt if something unexpected happens? Or is that where branching comes in?
That's a fair question. It is structured, but it's not totally inflexible. Routines can include branching logic. So think like different paths in a workflow. You might see a step labeled branch X1 step 1 that only runs if a specific condition is true.
So it can handle different scenarios within one routine. It's not just a straight line.
Exactly. It allows for dynamic, adaptable plans. It's not just a static one-way street.
Okay, so for you listening, maybe you're a developer, maybe a business leader, why should you care about this structure? What's the real benefit here?
It's really about building AI workflows that work reliably now, but are also easy to maintain and adapt later. Future-proofing? Kind of.
How so?
Well, the structure means the AI gets crystal clear instructions. It makes tracking the progress of a task much simpler. And, maybe most importantly for developers, it makes adjusting workflows way easier.
Easier how?
You can just insert a new step, delete one, edit the details, almost like editing text in a document, rather than having to rebuild a complex system from scratch.
Right.
It gives you agility.
Agility built into the AI's process saves time, saves headaches down the line.
Exactly. Countless hours, potentially.
All right, let's get to the proof, the numbers. This is where things got really interesting in the research, right? The impact.
Oh, yeah. The impact was, well, pretty dramatic.
Tell us about it, that HR agent application scenario.
Right. So routines significantly boosted execution accuracy. Take GPT-4o, a top-tier model. Its accuracy on these tasks jumped from about 41%.
Which isn't great for enterprise tasks.
Not at all. From 41.1% up to 96.3% when it was guided by a routine.
Wow, that's huge.
It is. And even for a smaller model, Qwen3-14B, its accuracy went from around 32.6% up to 83.3%.
So routine basically leveled the playing field almost. Made the smaller model perform nearly as well as the big one.
In these specific scenarios, yes. It effectively compensates for the planning weaknesses, even in smaller models. It lets them achieve performance close to the top models. It's like a performance booster for their planning skills.
A force multiplier, you called it. And when they looked at why the models were failing without routine, what was the main culprit? What did routine fix?
The biggest issue by far, over 85% of errors, actually, was tool selection errors. Meaning the model either picked the completely wrong tool for the job or just didn't pick any tool when it should have.
And routine solved that how?
By explicitly telling it which tool to use in each step. It basically changed the task for the AI. Instead of a hard reasoning problem, which of these 50 tools is right, it became a straightforward execution task. Okay, use this tool now.
Got it. Took the guesswork out. What about those branching scenarios, though? The ones with more complex logic. Was the performance boost just as good there?
That's an interesting nuance. So while routine helped everywhere, the performance lift was generally higher in scenarios without branching.
Okay.
Especially for the, let's say, average performing models. When you introduced branches, their accuracy dropped off more noticeably compared to the simpler tasks.
What do you think that is?
It suggests that branching works best when the model already has a really solid ability to follow instructions and call tools correctly. Adding branching is like adding another layer of complexity. If the foundation isn't rock solid, it struggles more.
So the underlying model capability still matters, even with routine guiding it.
Absolutely, especially for those more intricate logical paths. Now, moving from why it works to how you actually create these, routine isn't just about the structure, it's also about optimizing how you get there. Manually writing out every perfect routine is robust, sure, but it's also slow and expensive.
Yeah, doesn't scale easily.
Right. So the research introduces AI-driven optimization. An expert provides just a simple draft, like the basic workflow idea.
Yeah.
And then a powerful model like GPT-4o, armed with some specific prompt templates, takes that draft and automatically refines it into a detailed, structured routine.
So the AI helps build the instructions for the other AI.
Exactly. It makes creating these routines much more efficient, much more scalable for businesses.
That's a really practical advantage.
Uh,
What about the execution part? You said the planning might need a big model, but does the execution, can we use smaller, cheaper models there?
yes, absolutely. That's another key efficiency game. Planning often does need those big, powerful models because it involves complex reasoning about the steps.
Right.
But execution, the main skills needed there are just following the steps in the routine accurately and calling the specified tools correctly. It's more about instruction following than deep reasoning.
So you can use a smaller model for that.
Precisely. You can use a smaller, maybe even specialized instruction following model for the execution module. This saves a ton on computing resources, inference time, makes it much more practical for real-world deployment.
That's smart. Divide the labor based on the complexity.
Exactly. And one small detail. This execution model typically doesn't even generate the final natural language answer you see.
No.
Usually there's a separate, dedicated summarization tool or step that takes the final technical result and turns it into a human-readable response. Keeps the execution model focused.
Makes sense. So smart allocation of AI power. And you mentioned specific training strategies, too, to make these execution models even better.
Correct. Two main ones stood out. First is common routine following fine-tuning.
Okay, what's that?
Basically, you train the model on a large data set. The study used over 4,200 of generalized routines. The goal is to make the model better at following any structured routine it's given.
Improve its general ability to follow these plans.
Exactly. The potential trade-off is that it might become so good at executing predefined plans that its ability to plan things autonomously might decrease slightly. It becomes more of a specialized executor.
Okay, that makes sense. What's the second strategy? You said it was particularly interesting.
Yes, scenario-specific routine knowledge distillation. This one is really powerful.
Knowledge distillation.
Mm.
Sounds fancy. How does it work?
You use a highly capable teacher model like GPT-4o, and you guide it with a routine to perform a task correctly multiple times. This generates a data set of perfect, stable, multi-step tool calling examples for a specific scenario, like that HR task.
Okay, so you get perfect examples from the teacher.
Right. Then you use these perfect examples to train a much smaller student model.
And the result?
The results were pretty amazing. The Qwen3-14B model, the smaller one, when trained using this distilled data from GPT-4o, it reached an accuracy of 95.5% on that HR test set.
95.5. That's almost the same as GPT-4o with the routine prompt.
Exactly. It essentially internalized the procedural knowledge from the teacher. It learned how to do the task correctly. So the smaller model became highly accurate for that specific scenario, even without needing the explicit routine prompt fed to it every time.
Wow, so connecting that back to you, the listener, it's like meticulously showing an intern how to do a complex process perfectly, just once. And then they've absorbed it. They can just do it reliably on their own after that without the step-by-step checklist every single time.
That's a great analogy. Yeah. They've learned the how-to. That's the power of this distillation approach for AI. It encodes the process.
Incredible. Okay, let's zoom in a bit more on the systems mechanics. Those 4 modules again: planning, execution, tools, memory. How does routine fit in and help them work together? Let's start with tools.
Right. So the tool module is often managed by something like an MCP server. Think of it as a central catalog for all the available tools.
A tool library.
Exactly. And
Wow.
each tool is defined very clearly. Its name, what parameters it needs, any constraints. Because the tools are so well defined here, the execution model, guided by the routine, only has to figure out 2 things. Which tool name from the routine do I call? And what parameters from the routine do I pass to it?
So it decouples the doing from the tools themselves.
Precisely. It makes the whole system much more flexible. You can add new tools, connect to new systems, update existing ones in the tool module without having to retrain the core execution AI model every time. It's very extensible.
Smart. Now, memory. You mentioned earlier that LLMs can struggle with huge amounts of context. Costs go up, accuracy can drop. How does the memory system in a routine-based agent help?
Yeah, memory is absolutely critical here, and there are specialized types. First, there's procedure memory. Think of this as the agent's long-term memory for how to do things.
Okay.
It stores the whole collection of routines that the agent knows for different tasks or scenarios. When your query comes in, this memory system acts like an intelligent librarian.
How so?
It quickly analyzes your request and retrieves only the single most relevant routine from its collection. It doesn't overwhelm the execution model with dozens of irrelevant plans, just the one it needs right now.
Keeps the AI focused, efficient, prevents information overload.
Exactly. Keeps it focused. And then there's the second type, which is quite clever, variable memory.
Variable memory. What's that for?
This is more like short-term, temporary storage. Imagine in a multi-step process, one step generates a really long piece of text, like paragraphs long.
Okay.
Passing that huge chunk of text as a parameter to the next step can cause problems. It might exceed the model's context window limit, increase costs, or even cause syntax errors if it's not formatted perfectly.
Right, I can see that being an issue.
So variable memory solves this. It stores that long piece of text and generates a simple key like a placeholder ID, maybe a variaffix text 001. The execution model then just passes the short key to the next step in the routine. Then, right before the tool in that next step is actually called, the memory module automatically swaps the key back out for the full original text value.
Ah, very clever. So the model itself never has to handle the full, long text in its main processing.
Exactly. It significantly cuts down on the context length the model sees, reduces token usage, and avoids those potential errors from handling large, unwieldy parameters.
So for you listening, think of variable memory like a super smart clipboard for the AI. It holds on to the big messy stuff and just hands the AI a neat little reference code when needed. Keeps things lean, efficient, and error-free.
Precisely. It's a key optimization.
Okay, we've seen routine works wonders. But what specific parts of routine contribute most? Let's dig into the ablation studies where they took parts away to see what happened. First up, those detailed input-output descriptions for parameters. How crucial were they?
The effect there was, well, varied. For the less capable models, adding those detailed descriptions was quite helpful. It significantly cut down on errors where they passed the wrong parameters to tools.
Gave them extra guidance.
Exactly. But for the really high-performance models like GPT-4o, the benefit was smaller, more incremental. They seemed to be able to infer enough about the parameters just from the step description and tool name already.
So helpful, especially for weaker models, but not the absolute game changer for everyone.
Pretty much. Some models were surprisingly insensitive to them, suggesting they figured it out anyway. It's a useful addition, but maybe not the most critical piece of the puzzle across the board.
Okay, but what about explicitly stating the tool name in each step? You hinted this was critical earlier. What happened when that was removed?
Now that had a huge impact. When they took out the explicit tool name from the routine step, all models except GPT-4o saw a significant drop in accuracy.
How significant?
Typically between 5% and 15%, which is a big deal in these contexts.
Wow, so what does that tell us?
It really highlights that providing the specific tool name transforms the task. Like we said, it changes it from a difficult reasoning challenge, which of these tools is best, into a much simpler execution task. Use this tool.
And GPT-4o was the exception. It could still figure it out.
Mostly, yes. It was an outlier in its ability to infer the correct tool even without the explicit name. But for almost every other model tested, telling it exactly which tool to use was highly beneficial, almost essential for top performance.
That really underscores the value of explicit instructions for most current AI. It raises that question, doesn't it? How much can we reasonably expect AI to infer versus how much clear guidance do they need to be truly reliable?
It's a key question for designing these systems, definitely.
Okay, so explicit tool names are vital. What about the source of the routine? AI-assisted planning versus purely manual or just letting the AI plan autonomously? Where did the best results come from?
Well, first off, even a basic user-drafted routine, just an initial, maybe incomplete plan from a human, provided really crucial guidance. It performed much better than letting the model try to plan everything entirely on its own, fully autonomous.
So even a rough human plan is better than no plan.
Definitely. But then the AI-optimized routines, where a model like GPT-4o refines that initial draft, they brought significant and universal performance boosts across all models.
Interesting. Universally better.
Yeah. And for some models, surprisingly, the AI-optimized routines actually performed even better than the meticulously handcrafted, manually annotated ones.
Really? Why would that be?
The hypothesis is that maybe the format generated by the AI optimizer was somehow easier or more natural for those other AI models to understand and follow compared to the human written version.
Fascinating. So AI optimizing plans for other AI can be highly effective, a viable path for scaling.
Absolutely. It shows AI assistance is a really efficient way to generate these high-quality routines.
But was it the absolute peak performance? Did the manually created ones still have an edge anywhere?
Yes. For the top-tier models, the ones with the highest capabilities like GPT-4o, the absolute best accuracy still came from the manually annotated routines created by human experts.
Ah,
Those subtle nuances, the deep domain understanding that a human expert can embed. The most powerful models can apparently leverage those fine details for that extra bit of performance.
so the takeaway is AI optimization is great, very scalable, maybe even best for some models. But for mission-critical tasks using the best AI, that final human expert review or creation might still squeeze out the absolute highest accuracy.
That seems to be the case, yes. A final human check on AI-optimized routines is probably a good idea for critical applications.
Right. Last piece of the puzzle then, the memory system again, specifically the procedure memory. What happens when the agent has multiple routines stored? Not just the single perfect one, but maybe a few relevant ones or even some distractors. Does more information help?
This was another really surprising finding from the studies.
Sure.
For the high-performing models like GPT-4o, they actually performed best when they were given only the single correct routine.
Okay, makes sense. Focus is good.
But when even just one incorrect or distractor routine was added to the memory recall, their accuracy dropped significantly.
So confusion sets in.
It seems so. But here's the really counterintuitive part. As they increase the number of recalled routines further, say, from 2, 1 correct, 1 distractor, up to 3 or 5, 1 correct, multiple distractors, the accuracy for some models actually started to recover.
Recover. That seems weird. Why would more potentially wrong information help?
The researchers hypothesize that with just one distractor, the model gets confused and maybe tries to incorrectly combine steps from both routines, leading to errors.
Okay.
But when presented with more options, maybe it stops trying to merge them and instead switches to more of a selection strategy. It analyzes all the retrieved routines and makes a better judgment about which one is the most relevant to the actual query, similar to how it might select a tool.
So it shifts from integration to selection mode. Interesting theory. What about the smaller models? Do they react the same way?
The smaller models showed more erratic behavior, more fluctuation. Sometimes their performance did increase slightly as more routines were recalled.
Increase. Why?
One idea is that seeing more routines, even if some are distractors, means they see common, correct substeps repeated more often. This repeated exposure might inadvertently help them learn or execute those specific common substeps more accurately, even if the overall plan selection isn't perfect.
It's like accidental reinforcement of good fragments.
Potentially, yeah, it's complex behavior.
So pulling this all together for you, the listener, what's the practical implication for designing these memory systems? More isn't always better.
Definitely not. It strongly implies that the agent's memory recall mechanism needs to be really precise. Ideally, it should aim to retrieve only the single most relevant routine for the given task. Precision in memory recall seems key to maximizing stability and performance, especially for the more capable models. Quantity can actually hurt if it's not targeted.
Fascinating stuff. Okay, let's wrap this deep dive up. To summarize, routine offers this well-defined, structured, pretty comprehensive planning framework. And the evidence shows it dramatically boosts the stability and accuracy of LLM agents doing complex, multi-step tasks, especially in messy enterprise settings.
Yeah. And a key takeaway is how it empowers even smaller, less computationally expensive models to achieve performance that gets remarkably close to the top-tier ones. It really helps deliver on that promise of AI for process.
Making sophisticated AI more practical.
Exactly. Now, there are limitations, of course. Currently, generating these routines still often starts with an expert draft, which limits how easily they generalize to totally new, unseen tasks.
Right, the creation process.
But the future work looks incredibly exciting. Researchers are exploring things like reinforcement learning to help agents learn and refine routines more autonomously, and also multi-agent systems.
Multi-agent, how would that work with routine?
Imagine a high-level manager agent that coordinates several specialized worker agents. It could potentially assign tasks and manage workflows using structured routines passed between them. The goal is even greater autonomy, better generalization, more adaptability, really complex workflows managed smoothly by AI teams.
Very cool. Towards AI that can handle increasing complexity with less direct human input.
That's the direction, yeah.
All right, that brings us to our final provocative thought for you, our listener, to mull over. If AI can now follow a detailed routine with such precision for complex business tasks, what complicated multi-step processes in your own work, or maybe even just in your daily life, could benefit from a similar, highly structured, almost AI for process kind of approach? Where could that level of structured execution make a real difference for you?